I appreciate the opportunity to present on this topic today, the topic of ketone bodies, the mechanisms to human application. And my work was done at the University of South Florida, and also some of the human studies we do in collaboration with a number of universities, including the Institute for Human and Machine Cognition. Before I begin, I want to quickly go through my disclaimers, disclosures, and conflict of interest, which would be that this is not medical or nutrition advice, is not to be taken as such. And I am a co-owner of the company, Ketone Technologies, LLC, and also have patents and patent royalties that support our research associated with ketone metabolic therapies. And these interests were managed by my University of South Florida, conflict of interest policy team. So traditionally, therapeutic ketosis is achieved with a ketogenic diet or ketogenic diets. There are a number of different diets being used. The classical ketogenic diet has a macronutrient ratio that's very high in fat. Approximately 90% of the macronutrient ratio is fat. And then we have later coming onto the scene was a modified version of the ketogenic diet known as the modified Atkins diet or MAD, and also a medium chain triglyceride diet that allows for more liberal use of carbohydrates. These diets are difficult, can be difficult for the patient to sustain for a long period of time. The macronutrient ratio needs to be strictly adhered to allow for the process of hepatic ketogenesis to occur, to produce hyperketonemia, which is an elevation of ketones in the blood. And we know that ketones are an alternative energy substrate that can provide alternative fuel for the brain, especially, but also the heart and the muscles. So this continuous suppression of insulin signaling needs to happen to sustain therapeutic ketosis. And it's often difficult because a small amount of carbohydrates can, for example, increase insulin and increase glycolytic activity, which can induce seizures again. One way to circumvent the dietary restriction associated with producing therapeutic ketosis is with agents like ketogenic fats, for example, medium chain triglycerides, and to a greater extent, exogenous ketones, which can come in the form of ketone mineral salts. The ketone bodies are combined with a monovalent or divalent cation, including sodium, potassium, calcium, magnesium, or a ketone ester. And these esters can be 1,3-butanediol combined with esterified to beta-hydroxybutyrate or acetoacetate, or there are ketone esters of glycerol, which can combine with beta-hydroxybutyrate. These can come in the form of powders, liquids, or capsules. And on the right, the image of the capsules would demonstrate a dosage needed 3 times a day, 10 grams of ketone ester, and that would be needed to administer 3 times a day to produce a level of hyperketonemia that would correlate to a ketogenic diet. So traditionally, we know that these ketones can, or being in a state of ketosis, I should say, changes metabolic physiology, and it changes the proportion of energy that's being used by the brain. And it transitions the brain from burning glucose as its primary energy source to ketones, which may not necessarily be its primary energy source in a state of ketosis, but it's definitely serving as an alternative energy substrate. And over the last 5 to going back to 10 years, we understand ketones not only as a alternative energy substrate that can perhaps even enhance brain energy metabolism, but we know that the ketone bodies have distinct signaling mechanisms. And work that we've done in a number of animal models has demonstrated that ketone bodies can decrease oxidative stress. And it can do that through a variety of mechanisms. One is enhancing mitochondrial energy production, really, and decreasing the amounts of superoxide anion being produced. We know that being in a state of ketosis, even with exogenous ketone supplementation, can decrease glycolytic activity and even lactate production. We know that therapeutic ketosis can change the neuropharmacology of the brain. Specifically, it can increase the levels of GABA to the level of glutamate ratio. And it can do that through a number of different ways, including increasing glutamic acid decarboxylase, an enzyme that converts glutamate to GABA. We know that there's an increase in adenosine signaling. Adenosine is the adenosine receptor, when it's activated, can increase the flux of potassium, and that can hyperpolarize the membrane potential and stabilize neuronal transmission. We've done a number of studies looking at inflammation. We know that systemic inflammation can be suppressed, and systemic inflammation is correlated with neuroinflammation, and a suppression of neuroinflammation may be an important factor in ketosis-induced anticonvulsant effect. And there's quite a bit of studies looking at the epigenetic effects of ketones or being in ketosis. So that can come from beta-hydroxybutyrate specifically, or metabolites that are associated with being in ketosis. For example, acetyl-CoA is elevated and may have some influence on gene expression. So we've done quite a bit of work in various animal models, and it's been very exciting over the last few years to see exogenous ketone administration being used in human studies. So a quick review of the current clinical trials on clinicaltrials.gov demonstrated that 79 studies came up if you search ketone supplement. And about 50% of those studies were ketone ester, and maybe about 50% or so were ketone mineral salts. And the dosage ranged from 141 milligrams per kilogram to 1,250 milligrams per kilogram for the ketone ester, and quite a big range. And the same with the ketone salt, quite a big range. If you look at all the studies, from 50 milligrams per kilogram to 1,250 milligrams per kilogram. The tolerability of these exogenous ketone supplements has been an issue in the past. A large dose of a ketone ester can produce nausea and vomiting. The same for a ketone mineral salt. The sodium load associated with a ketone mineral salt can be quite problematic, especially if it's a pure sodium beta-hydroxybutyrate. So it's important for these formulations, what people have found, what we have found in our animal models and also in the human studies, is that you need a balanced mineral salt preparation. Sodium ideally balanced with potassium, calcium with magnesium. And if you spread the ketones over a range of monovalent and divalent cations, that can allow for greater doses. And if the ketone mineral salts are combined with medium chain triglyceride oil, remember MCT oil is a ketogenic fat, you can increase and sustain hyperketonemia over time. So you can get a higher dose of ketones if you combine ketone salts or ketone esters with medium chain triglyceride. You can get higher levels of ketone than if you use either one alone. So we're realizing now that combining these things may be the ideal way to go. But we're really at the cusp of understanding how to implement these things, especially for different disorders. So I'm currently involved in 3 projects, and 2 or 3 other projects will be coming online soon as a co-investigator or a consultant, including the use of a ketogenic diet. And more recently, we added ketone supplementation to this study for the reduction of central nervous system oxygen toxicity seizures in working divers. This is being done at Duke University. This particular study is using sodium and calcium beta-hydroxybutyrate combined with medium chain triglycerides, just 7 grams of each, given once 1 hour before a subject is immersed inside a hyperbaric chamber and pressurized to induce to induce EEG activity that would simulate an oxygen toxicity seizure. So we take them right to the brink of a seizure, and we look at the latency to seizure activity with and without being in a state of therapeutic ketosis. The therapeutic ketosis is induced with 72 hours of a ketogenic diet, and then it's just a single dose of a exogenous ketone preparation 1 hour before the oxidative stimulus. We also have a study on nutritional formulation for Angelman syndrome. About 85% of patients with Angelman syndrome have severe epilepsy. So this is using a balanced mineral preparation of beta hydroxybutyrate combined with medium chain triglyceride. And I'm a consultant on a study looking at the dynamic connectivity under metabolic constraints using a ketone ester, a monoester of beta hydroxybutyrate. The data from this is coming out now, just published in PNAS, and really demonstrates an increase in brain network stability when you induce a state of ketosis, especially relative to giving glucose. So brain network stability, which could imply increased homeostasis, is quite significantly higher in a state of ketosis. So we're starting to understand how mechanistically in human studies using PET scans and also using functional MRI, how ketones are altering brain activity. And a quick snapshot of the current trials online demonstrates that, and this has really dramatically increased over the last 1 or 2 years, the current applications for exogenous ketones include epilepsy and concussion. These studies will be coming online soon and added to clinicaltrials.gov. There's triheptanoin being used for glucose transporter type 1 deficiency syndrome. There are studies on Alzheimer's disease, Parkinson's disease, withdrawal. There's alcohol withdrawal is being studied, diabetes type 1 and 2, quite a bit of exercise studies being done, and studies on cardiovascular function. So this is a snapshot of the just an overview of the mechanisms that we know are associated with ketone therapy alone, and also an update on the what's being done in regards to human administration of ketone therapy. And that concludes the talk for today.